Swayam Prabha. Digital India. Educated India.
Maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a booming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected capacity building in this program. Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory, is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature of testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength does not degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state of art projection facility and good audio visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So, it is a state of art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around the advanced material manufacturing units. So, you will have state of art facilities available at IIT Gandhinagar. So, welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So, please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the lecture 17 on the course Maritime Structures under Fire, Blast and Explosion. In this lecture, before we start understanding the design for fire, we have learnt how the fire load can be estimated. Now, we will go forward to understand little bit more consequences of fire, because that is important to know the severity and the necessity for designing any system for fire resistance. So, welcome to lecture 17, Fire Consequences, under the SwayamPrabha course title Maritime Structures under Fire, Blast and Explosion. This curve is the one which is repeated from the last lecture, but with a small variation that I am showing 3 curves here. One is the natural fire curve, which has a backbone of decay stage. The other one is the standard fire curve, which has no backbone of the decay. The third one is a parametric fire curve, which has shown some decay. Okay, this is a new one which I have added to this. So, this parametric fire curve for structural design is recommended by Eurocode 1991-112
and annexure A. So, this also again starts after the ignition and smoldering stage, about 20 minutes, and the temperature is likely about 600 degrees Celsius, and structural fire engineering starts from this place onwards. Therefore, the parametric fire curve also starts, but the only thing is, after reaches certain stage and intersects with the natural fire curve, the growth phase, then the decay phase is added. Okay. This was not present in the standard fire curve model, which has been recommended by ISO. So, the parametric fire curve considers the effect of fire, the flood, fire load energy density, the room geometry, opening and wall materials. Therefore, it is expected that there will be some decay phase available for a given fire rating. It comprises of both heating and a cooling phase. So, this is a standard time temperature curve, where time is an x axis and temperature is an y axis, and the parametric fire curve recommended by Euroco for design has also the backbone or the decay stage of the curve, which was not there in the standard fire curve. Having understood this, let us now talk about fire protection. In fire protection, it is not necessary for each generation to rediscover the principles of safety. These principles already exist, we need to only learn them. Code requirements and regulations are based on past experiences and case studies. Past accidents need to be understood to realize the problems and then evolve good practices and regulations. Friends, firefighting, structural fire design and fire protection are analogous, and they are not based purely on experiments. They are more based on experience and good practices which have been used and visualized in various sectors, not in particular only maritime industry. So, it becomes very essential for us to look at a few case studies where fire occurred and what were the good lessons and practices which we could extract from that, or any bad practices which was resulted in that accident which we could avoid. So, one form of looking at the structural fire engineering is to design the system for worst scenario of fire, which is purely hypothetical, which is not practical. Practically, a good fire resistant design is always coupled with good practices and regulations to be followed in the workspace. So, this lecture is dedicated to how to learn good practices and regulations from various accidents or case studies which happened elsewhere. In this list, let us look at the first case study. You can see the photograph shot on February 20th, 2003 at about 11:30 p.m. in the night. Is actually a station nightclub in Rhode Island, USA, which got completely engulfed in fire. It resulted in hundreds of fatalities. The Life Safety Code NFPA 101 is interestingly revised based on or after this incident. Okay, it was revised based upon the catastrophic event outcome of this incident, and many safety practices and methods were made compulsory in NFPA, that fire life safety code, after this incident. So, accidents do not only cause catastrophic losses, they also add value to academic content of design codes of practices. So, new regulations were imposed on ingress arrangements, lining materials and so on. Most importantly, friends, sprinklers were made mandatory in commercial buildings and academic buildings of enclosed space after this incident. Earlier sprinklers were optional, now they are mandatory in NFPA. So, this becomes a good example of how case studies can be used to improve fire life safety of future occupants. Okay, there is a loss, they understand, and we feel sad and sorrow for that, but however, it has also given us a good lesson of importance to improve fire life safety of future occupants. Case study 2 happened in London 2003. So, Grenfell Tower fire 2017 was again a report generated on this. The external insulation and cladding which failed on this building, you can see this building has got lot of cladding on all the peripheral surface of the building, they all failed. We have already seen one example in the last lectures, which we have also conducted 1:1 scale experiment in fire engineering simulation laboratory, research laboratory at IIT Gandhinagar, where in about 17 minutes of start of fire, the fire spread to the second floor of a building, and where the cladding on the ground and first floor completely got destructed. So, it is not a news that the whole building of 22-story got set fire ablaze completely, and it resulted in about 72 fatalities, a big number. Life Safety Code imposed new building laws after this. The Life Safety Code compelled enough spaces around the building for firefighting. You can see the congestion around the building, which did not allow or permit the firefighting units to go closer to the building. So, after which the regulations were completely stringent, and they said for fire building, if the height is h, you must at least have 1/3 of h around the periphery of the building, which is empty and free accessible space, not for car parking, not dumped with any other equipments in electromechanical equipments, machineries, etc. Free space, mobility where firefighting engines can get in with larger gates of access and fire hydrants on the sides to supply water to the firefighting engines. This was made imposed as a regulator in the Life Safety Code after this incident. So, one important lesson learned from this incident is a geometric space around the building becomes very important, which is usually called as a circulatory space in architectural design, but in fire resistant design it is inevitably required to allow the access of firefighting engines to go around the building and do firefighting. It is also made legal that all fire accident reports should be made public, so that people will know what happened, who is accountable, and that should be transparent. So, the Life Safety Code also compelled the owners or the clients to publish the accidental reports with full details and made them public. That is how we got this information from the open source, where this can be reported easily. So, proper understanding of causes and consequences on buildings help the stakeholders like us to avoid mistakes and improve our knowledge. Guidelines for accident reporting in case of fire was not existing earlier, but unfortunately even in many developing countries, fire reporting accident format is still not available. People are still hesitate to share information because they are fearing of negative publicity. Friends, it is very important to learn correct practices of accident reporting and make it available to all concerned stakeholders, so that from these mistakes people only learn, they do not criticize, and there is no negative publicity of this. So, let us look at a detailed case study of one which happened in Plasco building fire in Tehran in 2017. You can see the complete building was devastated like an earthquake or any natural disaster. So, the whole building was brought down because of fire. Because of fire, the whole building was brought down. You can see the flame started here, spread upward. You can see the smoke which is spreading, and this is where the vapor cloud explosion things happen. Okay. You can see there are lot of plastic deformation happening in the buildings. building elements and it completely got collapsed. Okay. Even adjacent buildings were also affected, though they are something intact, but still some of them are affected. Okay. So, Plasco building fire happened in Tehran in Iran 2017. We will take up this for discussion now. Plasco building fire happened on January 19, 2017. The suspicion was an electric fault which caused fire later. It was a 16-story building on the capital city of Tehran, on Iran. Tehran, the Plasco building is in Tehran, it is the capital city. It resulted in complete collapse. Okay. 22 people reported dying, including 16 firefighters. More than about 200 people were injured, as the report says. The most important part, which is the highest concern, is the financial damage is projected to 3,800 crores of Indian rupee. So, the asset damage is more of concern for us, because we are dealing with maritime structures where we are talking about our oil and gas assets. In the current scenario, you would realize that 1 liter or 1 barrel of oil is as good as gold. It is very expensive now. You must have seen the latest trend, how the oil market is getting boomed up. So, the devastation caused by fire on oil platforms or even the stock areas where the port and harbors used to stock the LNG and CNG units or the processing units, etc., if they are subjected to fire accidents, there will be a huge financial loss. It can even lead to an economic setback to the country. In this specific example of Plasco building, most of the shops and business units were not insured and they did not meet any safety standards. So, these are all very interesting logistic part of the fire safety which one need to follow. Building was one of the tallest buildings in Tehran, built in 1960 by a prominent business firm called Plasco. Initially, it consisted of 5-story podium and a 16-story tower, with the structure as basement, ground floor and 14-story above the ground. It is a steel structure with concrete composite slabs. 4 internal columns carried the main vertical loads, while the primary beams and box columns are constructed along the perimeter of the building. All steel sections were fabricated by welding standard European channel or angle profiles. So, the building was designed perfectly with all advanced design methods and materials. Building can be categorized as a mixed use building because it has got shopping center, clothing workshops and offices. Now, this is an issue for fire load, whereas fire load, as you have learned, is actually calculation of mass and the calorific value of the product. In case of any mixed items like this, it cannot be categorized as residential or commercial. Therefore, the regulations do not apply to these kind of hybrid forms. That is another issue here. And this not only happened in Plasco building, it is a very common thing in all developing countries, especially in capital cities or very business centers. Tokyo, China, Beijing, even Bangkok, Thailand, even New Delhi and Bombay in India. You have what all hybrid mode of operations in most of the cities. It is not new only to Plasco building. The lower floors and podium initially were having only supermarket, while the upper floors had offices, but in due course of time, the whole building was taken and converted to manufacturing workshops, and that caused electric spark, and that was the reason for fire. And this conversion of the mode of operation has increased the fire load density inside the building. Remember friends, it is one of the important commercial complexes of the city and a landmark structure in Iran. This was completely brought down to debris in a fire accident caused by a simple electric spark happened in the building. Building had no active or passive fire control protection systems. They were not installed. There were no extinguishers or sprinklers installed in the building. Structural steel members did not have any kind of passive protection. Fire actually started on 10th floor, not on the ground floor. Due to electric short circuit, you can see that photograph here, it is on the upper floor, okay, not on the bottom, on the upper floor. It started on the 10th floor due to short circuit, early 8 o'clock in the morning, local time. So, there were few people around, fire remained unnoticed for a long time till it grew and sufficient quantity of smoke was released from the building. Fire spread quickly to other floors due to material being stored everywhere, and there was no horizontal and vertical compartmentation. This is another important design aspect in firefighting or fire resistant design of structures. The building should have vertical and horizontal compartmentation. Of course, this is not directly applicable to maritime structures because we talk about open workspaces, but still the strategic equipments, signal processing units and other intranet facilities should be compartmentalized and they should be protected from fire. So, the change of mode of operation in the building resulted in severe fuel loading. The fuel loading estimated to be 1100 megajoules per square meter. This is actually square meter, okay, it's 1900 megajoules per square meter. That is the load estimate on the floors. Now, since the building is open to all the four sides, enough oxygen supply was available through various ventilations. Therefore, fire grew very quickly and flashover took place in few minutes because there were no compartments. Flames could be seen projecting outside from 4 windows. Due to lack of vertical compartmentation, hot smoke and convection heat travelled through the shafts and ignite the stored materials in different parts of the floor and different floors as well. Building had no active protection, so it has resulted in a severe activation. By the time when fire service responded to the incident, 10th floor completely covered with smoke, so one cannot access to this floor at all because smoke is a big danger in case of fire. So, external firefighting was attempted. At the beginning, the fire on this floor appeared to have controlled, but the fire was kept on growing passively and start travelling in the upper floors. Fire service began to use aerial ladders and elevated platforms to control fire, but they could not put cooling material inside to control fire. Firefighting continued for almost 3.5 hours, but ultimately the full building collapsed. So, let us talk about the structural collapse of this specific case. Even when firefighting operation was going on, building collapsed. So, the structural fire engineering was not a focus at this design. So, we all know steel degrades faster at higher temperatures. So, the building was designed in such a manner that the load carrying elements were only vital of about 4 or 6 in number, rest were circumferentially built with claddings. So, they were steel and not protected passively and actively. Therefore, the steel lost its strength and that initially resulted in collapse of the building. The building collapsed progressively beginning from upper floors and the lower floors start collapsing in matter of seconds. The cause of progressive collapse was because of collapse of one major beam on the 12th floor. So, this was failed at the beam column connection. Impact of accumulating weight of collapsing floor on its lower floor caused collapse of ground floors as well, and therefore, the whole building was brought to debris. The detailed structural analysis as reported in the literature revealed that when the beam is axially restrained in presence of large deflection under fire, connections experience catenary force at high temperature. This is a very good lesson learnt from the technical perspective. Since the connections are not typically designed for interaction of these kind of other forces and catenary forces, they fail, and this caused the total collapse. Therefore, this factor needs to be considered in design standards and guidelines. What are the lessons learnt from this detailed example and the previous cases? Structural fire protection, that is adequacy for fire resistance to structural members, is critical. It ensures structural integrity during fire exposure. Unprotected steel members will fail quickly in fire, and they will cause the whole structure at a higher risk. So, one should not do fire resistant design only for selective members, because the other members are not protected. If they collapse, they will cause a dead load on the rest of the members and they will tend to collapse. That is what we learned from this lesson. Change of occupancy is another menace in this building design, which increased the fire load density. The fire load density went almost 3 times beyond the capacity of design, because the offices were all replaced with garment workshops. Added fire load resulted in longer duration, more intense fires, where the structure could not withstand this load. Lack of compartmentation, both vertical and horizontal, is another issue which allowed fire to spread horizontally and vertically to upper floors. Had the fire been restricted to affected areas, controlling fire would have been easy. Providing sprinklers and other fire protection systems were very necessary, which was absent in this building. So, lack of sprinklers allowed the fire to grow unhindered, where it went beyond the firefighting capability. Therefore, the building cannot be rescued. Housekeeping and fire safety management becomes very critical, especially when the buildings grow older. Careless storage of material improved the fire load density. In fact, in this building, interestingly, reports say even on the staircases, people dumped material. So, there is no escape mechanism at all. It resulted in abnormal heat exposure of the structure, and that caused a catastrophic failure to this. So, friends, let us come to the summary of this, what we have learnt in this lecture. Before we do a detailed fire resistant design, it is important that we learn certain lessons from fire accidents. So, in this lecture, we picked up 2 fire accidents and we understood that the reason of geometric spacing around the building, sprinkler designs, firefighting equipment design were necessary. In fact, NFPA safety against fire codes were revised, were updated based on the lessons learned. From one of the recent lesson of Plasco fire which happened in Iran, we understood that all members of such important buildings should be designed for fire resistance. You have no choice of designing only few members for fire resistance, because other members will structurally collapse, and that can cause heavy load on the other members, which can lead to damage of the whole building. Mixed user operation of the building, usage of the building will increase the fire load energy density or the flux. The fire load increases higher times, and that will cause worry. Thirdly, steel gets degraded with temperature rise, and steel cannot sustain additional load caused by thermal stresses when the load increases manifold, as in this case. So, fire resistant design is of course an analytical procedure, no doubt about it, but this is always substituted by good practices of design which are learned from such lessons. So, friends, you hope you have followed this lecture and you would have been thoroughly revisiting the previous lectures for a good continuity of this, and we will take you forward to understand further more detail about fire resistant design and explosion and blast resistant designs in the coming lectures. Thank you very much. Namaste.